With Nagarro's diverse range of resilience engineering services, you can build robust and reliable systems and ensure business continuity. Our tailored solutions ensure that your brand has the unbeatable advantage of staying at the top, even during unforeseen events.
Alright, so hey everybody, hope you're having a great time at Chaos Carnival 2023. This is Sarna, your host for the session, and I'm a senior software engineer at Harness and also the maintainer at Litmus Chaos. And I would like to thank our sponsors for sponsoring our community and this event. And so this session is on shifting left chaos testing by Pablo Chacin, who is the technical lead of chaos engineering at Grafana Labs/K6. And he will be with us to answer any questions at the end. So without any further delay, let's get started.
Hello, my name is Pablo Chacin. I'm the Chaos Engineering Lead at K6 Grafana Labs. Thank you for joining me in this talk. I will be talking about what makes achieving reliability in modern applications hard, and how chaos engineering emerged to help organizations to improve their resilience to failures. I will also discuss why, despite these promises, many organizations may find it hard adopting chaos engineering. I will then introduce chaos testing as a foundation to facilitate the adoption of chaos engineering early in the development process. Finally, I will exemplify the principle of chaos testing with a case study and will demonstrate how the open source reliability testing tool, K6, can be used for developing chaos tests. Why achieving reliability in modern applications is hard. The de facto standard for modern applications is a microservices architecture that leverages cloud-native technologies. This architecture has many benefits regarding its scalability and the resilience to failure of individual components. But it also increases the complexity of these applications as a result of the dependency between components and also the continued changes in their infrastructures. This complexity makes it difficult for engineers to fully predict how the application will behave in production and how they will react to abnormal conditions. For example, the failure of a dependency or the congestion of an infrastructure resource. Under these conditions, applications frequently fail in unpredictable ways. In many cases, these failures are the consequence of misconfigured timeouts and inadequate fallback strategies that create retray storms and cascading failures. This can be considered defects in the application. Unfortunately, traditional testing methodologies and tools do not help in finding them, mostly because they manifest in the interaction between services and are triggered on the specific condition in the load patterns, resource utilization levels, and timing of the faults. Implementing tests that reproduce these conditions is difficult and time-consuming, and more likely, the resulting tests will produce unreliable results because they suffer the same unpredictability that the application we are testing. Now, if failures are unavoidable and hard to predict, how organizations can improve their ability to continue operating in the presence of these failures? The most common way is by battle testing their applications, procedures, and people. By implementing well-structured post-incident reviews and adopting a blameless culture, organizations can learn from incidents and improve their ability to handle them. But incidents are not the best learning tool. They are unpredictable. You cannot decide what or when to learn. They introduce stress to the people involved. And at the end, the focus of the response team is to keep the business running. All these factors limit how much the organization can actually learn from incidents. So why not reproduce these incidents on purpose? In this way, the incident response team can be prepared in advance and test their procedure with less stress. This is a better way for learning, but there are still risks, mostly in the initial stages, when these procedures are not well tested. Also, there is a limit of the number and type of incident organizations can try before affecting their service level objective. Another limitation is that these games are preparing the organization for situations they have already experienced or can predict somehow. But as we discussed previously, modern systems sometimes fail in novel ways. more so as the dependency between services and the configuration of the underlying infrastructure evolve continuously. Therefore, we need an approach to learn how the system fares under unexpected conditions. Chaos engineering is a discipline that emerged as a response for this need. It builds on the idea of experimenting on a system by injecting different types of faults on the production environment to uncover systemic weakness. For instance, killing or overloading random computing instances, or disrupting the network traffic. And doing this in a continuous way, making fault the norm instead of the exception. In this way, developers get used to facing faults and therefore will naturally consider recovery mechanisms in the design of their applications, instead of introducing them later in response to incidents. This approach has been championed by companies such as Netflix with its iconic Chaos Monkey. But despite its promises, some obstacles still remain for chaos engineering to be adopted by most organizations. First, chaos engineering set a high adoption bar by focusing on experimenting in production. And we cannot argue against this principle. Nothing can substitute testing the real system. If we could reproduce incidents on other environments, we would not need these chaos experiments in the first place. Unfortunately, many organizations are not prepared for taking this approach. Their procedures may not be sufficiently tested, and therefore the engineering teams may lack confidence in their ability to contain the effects of such experiments. Another significant issue is the unpredictability of the blast radius of the chaos experiments. Killing or overloading instances of disrupting the network traffic may affect multiple application components, introducing unexpected side effects. Moreover, modern infrastructure has many recovery mechanisms that may come into play and interact in complex ways. All these factors make the result of the experiment hard to predict. And this is part of the idea. This is what is called chaos engineering after all. But this is difficult to test recovery strategies for a specific situation if you cannot reproduce it consistently. Finally, adopting chaos engineering tools can also be challenging. Installing and using them sometimes require a considerable knowledge on infrastructure and operations. And it makes sense as chaos engineering has its roots in the SRE and DevOps communities. However, this complexity raises the adoption bar for most developers that cannot be self-sufficient for using these tools. In summary, chaos engineering requires a level of technical proficiency and maturity that many teams and organizations do not have. So, how more organizations can start building confidence in their ability to withstand failures? Is there an alternative to jumping into chaos engineering in production? We propose shifting chaos testing to the left, incorporating tests early in the development process to validate if the application can handle the conditions created by incidents in an acceptable way. And if the results do not meet expectations, use this test for validating alternative recovery strategies. At the core of chaos testing is fault injection. Fault injection is the software testing technique of introducing errors to a system to ensure it can withstand and recover for those conditions. This is not a novel idea. It has been used extensively in the development of safety-critical systems. However, it has generally been used for testing how applications handle isolated errors, for example, processing corrupted data. Can this approach be effective for testing modern applications? Can we use it for testing the complex error patterns that emerge from the interaction between components and from the changes in the infrastructure? Fortunately, as explained in this quote from two former members of Netflix Chaos Engineering team, from the distributed system perspective, almost all interesting availability experiments can be driven by affecting latency or the response time. In other words, we don't need to kill instances or saturate resources expecting to generate the faults we want to test. We can instead simply inject changes in these two parameters, latency and the response type, to simulate faults. Later in this presentation, we will discuss how this can be achieved using cases. But at the beginning of this presentation, we said the main challenge of modern distributed applications was their unpredictable behavior under turbulent conditions. Therefore, it is valid to ask, what benefits can we expect for testing known faults in controlled development environments? will this really contribute to improving the reliability of the applications, or will it only create a false sense of confidence? According to a study of failure in real-world distributed systems, 92% of the catastrophic system failures were the result of incorrect handling of non-fatal errors. And in 58% of the cases, the resulting fault could have been detected through simple testing of error-handled code. Moreover, in 35% of the cases, the error-handled code fell into one of three patterns. It overreacted, aborted the system under non-fatal errors. It was empty or only contained a log printing statement. It contained an expression like "fix me" or "to do" in the comments. What this study comes to tell us is that there is a significant room for improvement in the reliability of complex distributed applications by just testing the error-handled code. And this is what chaos testing proposes. Incorporate the principle of chaos engineering early into the development process as a fundamental part of the testing techniques, shifting the emphasis from experimentation to verification, from uncovering unknown faults to ensuring known faults are properly handled. By adopting chaos testing, teams can build confidence for moving forward to chaos experiment in production, and then use the insight obtained from this experiment and for incidents to improve their chaos tests, creating a process of continuous reliability improvement. In order to achieve its goal, chaos testing is sustained in four guiding principles. Incremental adoption. Organizations should be able to incorporate chaos testing in an incremental manner, starting with simple tests so they can validate how their system handles faults, and then building more sophisticated test cases. Application-centric testing. Developers should be able to reproduce in their tests the same fault pattern observed in the applications using familiar terms such as latency and error rates, without having to understand the underlying infrastructure. Chaos testing as code. Developers should be able to implement chaos tests using the same automation tool they are familiar with. Switching between application testing tool and chaos testing tools will create friction in this process. And as we discussed before, it may reduce the autonomy of developers for creating chaos tests. Control chaos. Faults introduced by the chaos test should be reproducible and predictable to ensure tests are reliable, because this is not possible to build confidence from flocky tests. Also, tests should have a minimal blast radius. It should be possible to run them in shared infrastructure, for example a staged environment, with little interference between teams and services. This will also facilitate including this test as part of the normal CI/CD integration test. Let's put this principle into action using a fictional case study. This case study used the Sock Shop demo application. This application implements an e-commerce site that allows users to browse a catalog of products and buy items from it. It follows a polyglot microservice architecture. Microservices communicate using HTTP requests, and it is deployed in Kubernetes. The front-end service works both as a backend for the web interface and also expose the APIs of other services, working as a kind of API gateway. Let's now imagine an incident that affected the Sock Shop. In this incident, the catalog service database was overloaded by long-running queries. This overload caused delays in the request, up to 100 milliseconds over the normal response time, and eventually made some requests fail and return an HTTP 500 error. The catalog service team will investigate the incident to address the root cause. However, the front-end team wondered how similar incidents would affect the service and the end users. To investigate this, let's start with a test for the front-end service that will serve as a baseline. This test applies a load to the front-end service requesting products from the catalog. The front-end service will then make requests to the catalog service. The front-end service is therefore the system under test. We will measure two metrics for the request to the front-end service: the failure rate and the percentile 95 of the response time for all requests. And we will be implementing this test using KSys. KSys is an open source reliability testing tool. In KSys, tests are implemented using JavaScript. It covers different types of testing needs, such as load testing, end-to-end testing, synthetic testing, and chaos testing, as we will be discussing next. Its capabilities can be extended using a growing catalog of extensions, including Kafka, NoSQL databases, Kubernetes, SQL, and many others. It can send test results to common backends such as Prometheus. We will be using this capability for visualizing the test metrics in a Grafana dashboard. Even when we are not going into too much details in this example, there are some concepts that are useful for understanding the code we will be discussing next. In K6, user flows are implemented as JavaScript functions that make requests to the system under test. The results of these requests are validated using checks. Thresholds are used to specify SLOs for metrics such as latency or error rates. Scenarios describe a workload in terms of a user flow, a number of concurrent users, the rate at which the user may request, and the duration of the load. Let's make a walk through the test code. We will just skim over the code, highlighting the most relevant parts. At the end of the presentation, you will find additional resources that explain this code in detail. The test has three main parts. A function that makes call to the front-end service requesting a product from the catalog. The function also checks for errors in the request. We define a threshold for the rate of requests that pass the check. If the ratio of successful requests is below this threshold, the test will fail. This is our service level objective. Finally, we define a scenario that describes how much load we will apply and for how long. Let's run this test and check the performance metrics. We can see that all requests were successful, and the latency was around 15 milliseconds. We will use this result as a baseline. Now, let's add some chaos to this test. This time, while the load is applied to the front-end service, we will inject fault to the request served by the catalog service, reproducing the pattern observed in the incident. More specifically, we will increase the latency and inject certain amount of errors in the responses. Notice that the front service is still the system under test. The catalog service is the target of the fault injection. For doing so, we will use the K6 disruptor extension. This disruptor is an extension that adds fault injection capabilities to K6. We are not going into the technical details about how this extension works. For now, it is sufficient to say that it works by installing an agent into the target of the chaos test, for example, a group of Kubernetes pods. These agents have the ability to inject different types of faults. And this is done from the test code, as we will see next, without any external tool or setup. At the end of the presentation, you will find resources for exploring this extension in detail, including its architecture. Let's see how this works in the test code. First, we add a function that injects the faults. This function defines a fault in terms of a latency that will be added to each request and the rate of request that will return a given error. In this case, we introduce a delay of 100 milliseconds per each request, and 10% of the request will return an error 500. Then, it selects the catalog service as the target of the fault injection. This instructs the disruptor to install the agent in the pods that back the service. Finally, it injects the fault for a given period of time, in this case the total duration of the test. Then we add a scenario that invokes this function at a given point during the execution of the test. In this case, we will inject the fault from the beginning of the test. And with the changes, we have a chaos test. Let's run this test and check the metrics. We can see that the latency reflects the additional 100 milliseconds that we injected. We can also observe that now only 89% of the requests pass the check. This is below the threshold of 97% of successful requests we define. Therefore, we are not meeting our SLO and the test has failed. Now, it's important to remark that we are injecting the faults into the catalog service, but we are measuring the error rate at the front-end service. So, we can see the front-end service is not handling the errors in the request to the catalog service. More likely, there are no retries over failure requests. How this test helps the front-end team? First, by uncovering improper error handling logic, as we just saw, and then enabling them to validate different solutions until they obtain an acceptable error rate, for example, introducing retries. They can also easily modify the test to reflect other situations, like higher error rates, in order to fine-tune the solution and avoid issues such as retry and storms. In summary, this brief example shows the principle of chaos testing in action. A lot of functional tests can be reused to test the system under turbulent conditions. These conditions are defined in terms that are familiar to developers: latency and error rates. The test has a control effect on the target service. The test is repeatable and the results are predictable. The fault injection is coordinated from the test code. The fault injection does not add any operational complexity. There is no need to install any additional component or define additional pipelines for triggering the fault injection. To conclude, let me make some final remarks. We firmly believe that the ability to operate reliably should not be a privilege of the technology elite. Chaos engineering can be democratized by promoting the adoption of chaos testing. But to be effective, chaos testing must be adapted to the existing practices of testing. In Grafana KCs, we are committed to making this possible, making chaos engineering practices accessible to a broad spectrum of organizations by building a solid foundation from which they can progress toward more reliable applications. If you want to learn more about chaos testing using KCs, you can use these resources. You will find an in-depth walkthrough the example we saw today, and more technical details about the disruptor extension. Thank you very much for attending, and I hope you have found this presentation useful.
Thanks, Pablo. Thanks for this talk. It was really helpful for us to know more about K6 and the chaos engineering. So we have few questions from some of the attendees. So I'll bring one by one. I think we have few minutes. So the first question is from Amit. So Amit, his question is how K6 and chaos engineering can be used in continuous testing and CI/CD pipelines. Sorry, Pablo, I think you are on mute.
Yeah, sorry. That's a quite interesting question because one of the objectives of when we designing this approach is that as you are running this as a scripts, and these scripts are defining some threshold for the say error rate that you can tolerate in the test, etc. That they can easily introduce in the pipeline because imagine you have a staging environment or an integration test environment. You can run this chaos test against this environment. And as I explained in the talk, you are not actually disrupting the environment, you're injecting faults in your test. So you basically run your test, you simulate there are some errors are happening. You are not really disrupting the infrastructure. You are not killing any instance. You are just simulating the incident or the situation by injecting faults. And once the test is over, the environment is totally functional again. So you are not having this issue that, for instance, you cannot run a chaos test in a certain environment. You are killing pods randomly because you are creating some disruption in the whole environment. So one of the ideas that you can put this test as part of your integration test suites, so to speak, and automate that easily. And because you are defining your acceptance of the test in terms of the SLOs, you can see if the test is passing or not uh, easily, automatically. You don't basically define my test will work if I have a error rate and successful rate of over 99%. Below that, the test will fail. And all that can be easily automated in the script.
Yeah, that makes sense. Yeah. So thanks, Amit, for asking this question. I hope you got your answer. So the next question is from Nilanjan. I'll just probably put it in the stage. So how team can communicate to their stakeholder and management about the result of chaos engineering and K6? So what are the metrics? I mean, uh, we
Well, I
can.
think this you see, This example, you see that the result of this test are being sent to a dashboard, and when you're
Hmm.
reflecting, there are actually SLOs. So the idea here is that you already have an SLOs of your system, which you have. So starting, you have the SLOs, you can create a dashboard for the SLOs, and you can basically send the result of your case test to the to this dashboard, so you can see what is your situation, real situation in production, but you can also see what is your situation after running the test. You can see, oh, I'm running this test, and for this test, I'm breaking my SLO. So that is telling me that I have a risk there, because if that incident happens, if that situation happens, I will break my SLOs in reality. So basically, the easiest way to communicate that is to creating a dashboard with the result of the test. So you can basically see which tests are failing, and therefore which system have a risk of actually failing in production if that situation happens. As an example of the presentation, if that situation happens, you will see that your system will fail. So that's a risk, and that's the way you communicate easily to management in terms of, see, here we have a problem. That has not happened yet, but if this situation happens, you will have a failure here. So you can help the management prioritize the investment in resilience based on the risk of the different system based on the tests that you're running.
Yeah, cool. Thanks, Pablo, for answering this question, and thanks, Nilanjan, for asking. Uh, I think we have crossed the time. I think we can take one more question, right, Saranya?
Yeah,
Yeah.
we can take.
So, last question. From John. Are there any tools, kiosk tools, which has been integrated with K6 till
Yeah,
now?
yeah. There are some tools, including if I recall correctly, Chaos Toolkit is integrated with us, and other folk have created some integration because, but that is running the case sheet from the Chaos Engineering or Chaos Experiment,
Hmm.
which is a different approach than what we are proposing is injecting defaults from the test. So the typical integration you see is that as a part of a chaos engineering experiment, you have some task that is injecting the load while you are running this experiment. Okay, if you go to the KC's documentation, the website, and you will see there are some integrations there. You can find some pointers to some integration. If or you can also ask in the community channel of KC's, and we also can point you to specific integrations depending on your needs.
Okay. Yeah. Thank you, Pablo, for answering this question again. I think we can close this session. Thank you, Pablo. Thanks for this talk, and I hope the uh, attendees will get a lot of things from this session. And thank you. See you in
Thank
the
you
next
for
session.
having me. Okay. Yeah.
Thanks, everybody. Bye bye.